Okay. Started. As they say in one Python, and now that's what they do. I know Arun Bala through various sort of channels. I think I first encountered him at a workshop that you maybe organized at the Asia Research Institute in Singapore, where Bala is a senior research fellow. But also, some of us know him because he was once and now again a visiting scholar at the Institute for History and Philosophy of Science and Technology at UOT. In fact, Baby Bala is an honorary Canadian because he got his PhD at University of Western Ontario in their famous philosophy of science group. Bala is known for several books, several workshops, and several things that he's done for the United Nations, including a wonderful database which is on hold for him on non-Western encounters with science. Is that what that was? Yes.
Yes.
You can talk about it later. He's the author of Asia, Europe, and the Emergence of Modern Science. A wonderful collection, The Bright Dark Ages, Comparative and Connected Perspectives, and especially the book that is known for, and creates wonderful controversies around the dialogues of civilizations and the birth of modern science. I'm sure we'll hear a bit about that today.
Well, thank you, Gordon. I hope I'll get this to work. Before I begin, I would like to thank the organizers of the conference, including Gordon, Melanie, Megan, and all the others. I won't repeat what I said earlier. So what I want to do now is to after listening to all the different talks that have gone on here, I feel kind of a bit strange about what I'm doing. It might appear to be like somewhat Eurocentric, talking about the scientific revolution and so on. But let me assure you, keep talking, that it isn't. That it isn't. Yes. And because I have, about 55 minutes, I guess, and I don't want to rush through this. Let me get on first by talking about a book an edited work that is coming out of a conference we organized in Hong Kong in 2023. And it's a collection of chapters selected from papers at that conference. Multi-civilizational exchanges in the making of modern science, edited by me and also by Raymond over there, and it has chapters in it which include a chapter by Gordon, another by Uni Park, who are all present at the conference, and also Peter Lee, chairman of the Joseph Needham Foundation, with which I am affiliated, has also honored us by writing a foreword to it, and they were very much involved in supporting the conference. Now, so when the book arrives, let's say about in October, I hope some of you might look at it. It's very related to the kind of themes that are being raised here at this conference. Now, let me go on now to the topic of my talk, which is a distinction I make between tunnel histories of modern science and a different kind of history, is circulation histories or cosmopolitan histories or dialogical histories, as I call them. And I won't go through this quote by Floris Cohen in in a book published about how modern science came into the world. There was later rewritten as a shorter version explaining the rise of modern science. A comparative perspective, I think it was entitled, where he thinks the Chinese tradition was, quite advanced because of its organic materialism over many years, but it did not have the potential to develop into modern science, and therefore modern science was very unlikely to have developed there. And another quote by Toby Hunt, who is also quite well known as sociology of knowledge, historian too. Intellectual curiosity and the scientific revolution, a global perspective. And he writes in that book, the present narrative will show whatever the glories of Asian China, India, or the Islamic Middle East, their contributions to the making of modern science were minor. And my paper is actually a response to these, because they see histories as running in separate civilizational tunnels, and their interest is in comparative history and not circulation history. Now, so what I want to do, and this is very much an exploratory paper, and it's not from my book that Gordon mentioned, the Dialogue of Civilization, because there I focus on mostly on astronomy and the astronomical traditions of various cultures and how they came into modern science, what they contributed. Here, what I want to develop is a dialogical view of 4 multi-civilizational transmissions into Latin Europe prior to the modern era. One is ancient Greek geometry, which entered Latin Europe about 1120 in the 12th century. Another is Arabic optics, which also entered Europe a little later, 12th to 13th centuries. And then the Indian number system, about the same period, in about 1202. And I will go into this in a while. And Chinese technologies from the 12th to the 15th centuries. Now, all of them entered Europe, and they became, sort of impacted Europe as sciences, but they also carried with them modes of thinking, ways of inquiry that became reshaped and then went into modern science. Now, and so as an exemplar of this, so, I choose Newton's Principian optics, 2 famous words, Isaac Newton, to illustrate the coming together of these impacts. So I will go through this in a number of stages, which, first, how were these traditions formed outside? How were they transplanted into Europe? How were they transformed within Europe? I don't need to go into the question of why they get transformed, but though I think I've attempted to answer. And then how they were integrated together in the Newtonian synthesis. So let me begin with Euclid. Now, why am I including Euclid? Isn't Euclid a part of Europe? Yes, Euclid is a part of Europe because of the Greek science heritage, but Euclid worked in Egypt. And secondly, the modern science that developed in Europe was very different from the Greek science. But the Greek tradition did have a major impact on modern science. And the impact of Euclid was in the area of geometry. And the distinctive Greek contribution, as I see it, is in mathematics, especially the mathematics of geometry. Now, all of us know when we learn geometry, you kind of prove a theorem that's very important. And the Greeks developed, both they were not the only ones, the notion of proof. The idea of proof was there in other places too, though they might be slightly different kinds of proof, but deductive proof was there. But what was, so the idea of deductive proof of theorems, other theorems was there, but the great achievement of Euclid, the exceptional achievement of Euclid was that he said, okay, theorems are derived from theorems. What were those earlier theorems derived from? They were derived from, you can prove them from prior theorems. But if you keep doing this, you will achieve infinite regress. So you must start from somewhere. Where do we start from? And Euclid introduced the idea that you start from axioms. Axioms are, for him, self-evident first principles. Okay. So what would be self-evident? Between 2 points, you can only draw one straight line. Okay. Or if you have a point and you give a radius on a plane, you can only draw on a plane one circle. You cannot have, if you draw it again, it will just go over that circle. And so on. I won't go into it. We have 5 axioms. But the important idea behind it was that geometry was a deductive science. It can begin with first principles, which cannot be doubted, indubitable, and which are self-evident. The moment you hear that, you say, yes, I agree, that's right. Okay. Of course, it could be disputed now with non-Euclidean geometries, but this was not there at that time, even conceivable, even at the time of Immanuel Kant. Now, the next tradition that was formed was Arabic optics. Now, and the famous name here is Ibn al-Haytham. Of course, there was a background to all this I won't go into. And he lived in the 10th to 11th centuries. And the optics in his time that the Arabic tradition and inherited, when I mean by Arabic, I don't mean Arabs, I mean people who wrote in Arabic, which could include Christians, Jews, Persians, and all kinds of people. Now, the tradition at that time was Ptolemy's theory, emanation theory. It's very simple. How do I see you? I see you because there is an emanation from my eyes that reaches out to you. Somewhat like a blind man reaching out with a stick. I could reach out with a stick and feel the objects in front, and I get a sense of what there is. And the reason this theory was adopted was because it created this visual code, and I won't go into the details, that allow a mathematical theory of optics. Now, Al-Hazan actually objects to that theory in his book of optics. He says, well, it's very strange, that you see objects through such an emanation, because it means when we see the stellar sphere, this emanation must reach out and fill the whole sphere, okay? Or what if it's an emanation, why can't we see objects in the dark? Because the seeing is a reaching out. A blind man can feel objects in the dark. Why not? The emanation theory should allow us to do that. There are a lot of other objections that he raised, and he introduced a very novel idea for that time. Of course, derived from Al-Kindi, an earlier Arabic philosopher, the ray theory, which is kind of taken for granted today. I'm oversimplifying it. Modern ray theory did not be exactly Al-Haytham's theory, but the idea is we see because every point in the world sends out rays that reach our eyes, and it sends out rays in all directions, which is why if I look at a person and I'm moving away, I still see the person because the rays are coming from all directions. And using that idea, he got back the visual cone of Ptolemy, but without the implausible idea, the notion of rays going out into the world from the eyes, but of rays coming in, which we take for granted for today, and captured all the mathematical power of the Ptolemaic theory, and so he was able to do something that Ptolemy wasn't able to do, the Greek astronomer, because, and of course, he worked in optics, because he was able to give a mathematical theory that was also realist. It was a real theory, so mathematical realism was possible. For Ptolemy, the theory, of emanations from the eyes was mathematically good, but from a realism point of view, it wasn't. Aristotle had a theory that of emanations coming from the object to the eyes, the whole form captured like a picture coming in, but you couldn't do a mathematical construction with it. Okay, the next great influence that I talked about, and how it was formed, Indian numbers. We all know the number system now. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. It is 10 digits, decimal numbers. The value of the number depends on its place, So in a number like 1729, the 1 in front is 1 times 10 cubed. The 7 is 7 times 10 squared, and so on. It's written as a power series. This is a very novel way of writing. You compare it with the abacus techniques, some mathematical operations or arithmetical operations, or the Roman numerals, for instance. And it expanded arithmetical computation power, but it also expanded the power of algebra. And even actually, I would say, made possible modern calculus. People have adapted it. Now, why was it so powerful? Because it built up the numbers as atomic units. First you have the ones, and then the 1 plus 1, and then the 1 plus 1 plus 1 makes 3. Once it gets to 9, then the 1 shifts place, becomes a 10, and so on. So it's like building up, something like the military battalions, organized into units of tens, hundreds, and so on. And this idea, that this was actually mentioned also by Al-Khwarizmi. And this mathematical mechanism is the unique achievement of the Indian number system. And the first important influence that went in was Chinese technologies. We all know about gunpowder, printing, the compass, the magnet, and so on. But the Chinese had many other technological achievements that entered Europe later. And it is related to the view of nature as an organic system. Okay, and this organic materialist idea was also developed and articulated by Needham, and that is, you must follow the way of nature. So what they do is study nature very carefully, and then kind of tinker and approve with it to see how it can be improved. Okay, and also with Moism, there was this idea of model thinking, that you work with physical models, technological models, and then you improve them by modifying them slightly and so on. And this kind of thing, over many years, with the support of the Chinese Confucian bureaucracy, and with maybe Taoist craftsmen and others working together, kind of a scholar-craftsman, or more like a bureaucrat-craftsman relationship, improved technologies gradually over hundreds and maybe a couple of thousand years. Now, what is this method? What do we call it? Well, today, many people connected with artisanal epistemology, perhaps we could, and I'm not doing that. And you can see it as a kind of a contextual experimentalism. You work within context, you experiment within them, and then you improve them again. And then what works, you keep, and then you go on doing that systematically. Contextual experimentalism. So you see, indubitable, all of the categories at the bottom, mathematical realism, these are philosophical, epistemological categories that we are talking about, that came with these transmissions, or that were there in the original. Now I want to look at, okay, these traditions that were formed, how were they transmitted to Europe? Now the Greek geometry was the first that was transmitted. It was translated into Latin. The Europeans at that time, at least the Western Europeans within Latin Europe, could not generally read Greek. Okay, it was part of a different civilization, at least they conceived it at that time, okay? Before it was reinterpreted in the scholastic era. Now, the first Euclidean translation was made by Adela Abba of Euclid's Elements in 1120, and he made it from the Arabic. And there were a couple of other translations maybe later that came, also made from the Arabic. Direct translations from the Greek tradition were only made after the 16th century. The fall of Constantinople in 1453, I think, and a lot of scholars flee from that area of the Eastern Roman Empire in the past, carrying Greek manuscripts with them. Now, these translations, even before the translation directly from the Greek came, made a major impact on scholastic renaissance. Okay, with people like, I hope I'm pronouncing his name right, Grosseteste and Roger Bacon, okay, who were then with the newly formed Oxford University. They were quite impacted by it, and there's a lot of writing in their, work that says, it talks about the importance of mathematics. Now, this Greek geographic tradition of Euclidean maths also went on to have an impact on artists, architects, engineers, and later on, it also began to impact people who were ordinary practitioners. Leslie talked about the ordinary practitioners, and because of that, they couldn't read Latin or Greek. Translations were made in their vernacular languages for them. This vernacularization, as a knowledge of this kind was needed by the practitioners who were not the scholars. And so there was an English translation by Henry Gillespie. Now, Arabic optics. It was also translated about the same time. Okay. It was the seminal period in the medieval era for Latin Europeans, at that time. Al-Haytham's book of optics was translated into Latin at the end of the 12th or early 13th century. And it became an authoritative text, people began into Latin, and people from the Arabic, and people began to write about these optics, and even translate these optics. People like Roger Bacon, people like John Patton, and people like Vitalo, okay? And there was a lot of interest in the optics, and it was the only really successful theory at that time, that was mathematically right and was physically plausible. And even Geoffrey Chaucer refers to Al-Haytham in the Canterbury Tales in association with people like Aristotle and Vitalo. Okay. And even in 1647, when Johannes Hevelius published his Selenographia, which is a book of the map of the moon, from the telescopic discoveries of Galileo, he also recognized that you could do the math by looking at the shadows of the craters and calculating how high or low they would be relative to the sun and shadows, using the optics of Al-Haytham. So he has a picture in front of the Selenographia that has Galileo holding the telescope on the one hand, underneath representing observation, and Al-Haytham standing on the other hand with a scroll representing reason. Okay, so even in 1647, in this influential map of the moon, the two traditions, the influence of Al-Haytham was acknowledged. Now, the Indian numbers, okay, they were also translated. Strangely, they all occurred about the same time. This was a very seminal period for Europe and for the circulation of knowledges from outside into Europe. And here it didn't occur through translations, but Fibonacci's Liber Abaci was published, Modus Interum, the method of the Indians, in 1202. Okay, and it was also later, there was translation from Al-Khwarizmi's book on the Indian numbers in the 13th century. Okay, now this number was very powerful, and you could calculate with a pen and paper. You didn't need an abacus, and it was far more powerful in doing operations like addition, subtraction, multiplication, division, compared to doing it in Roman numerals, for instance. Okay. And this power went on. Cartesian geometry, we all know a straight line is ax plus b equals something, okay, or 0, okay, or x squared plus y squared equals something r squared, okay, is a circle, So Cartesian geometry actually uses algebra to represent geometric curves, okay, and geometry to represent algebraic equations is actually a combination of the Greek and the Indian tradition. So it was a very powerful synthesis. And I won't go into that, but the numeric impact, I call it numeric impact because it's more than just arithmetic. It went into algebra and later it made possible the calculus. You have a figure in the Margarita Philosophica I could show you of two people, Pythagoras using the abacus, which he probably never used, and Boethius, calculating with the Indian numbers, which he probably never did either. But it shows, the comparison of the two traditions. I have a thing here to show you that at the time. Now, the last transmission was Chinese technologies. Okay. Now, Chinese technologies actually went way back into Roman times. Okay, because there was a trade, silk trade, The Romans complained about the drain of their silk, okay, because of the demand for silk at that time. And until they discovered a way of smuggling silkworms into the Roman Empire in the 7th century. And then they started to make silk industry, and you could have money in Europe without needing to transport it along the long route from China to Europe. But the more important thing, okay, that kind of technological exchange was going on very gradually all the time. But the main inventions we think of, like the compass, the gunpowder, hand cannon, the printing press, which was developed in Europe in 1439, but in China, movable type printing was developed in the 11th century, about 400 years earlier. Now, these inventions also occurred over this kind of pre-modern period. So, and Francis Bacon talks about this. I won't go into that. He says there has been no greater influence on human affairs in his Novum Organum, published in 1620, than these three, he calls them mechanical inventions, and maybe rightly so. Okay, so these are how the four traditions came to be transplanted into Europe. But the Europeans did not receive the four traditions passively. Like it was not just they were transplanted, we learned the tradition, and then we learned the kind of modes of inquiry or with that went with them, their methodology, whatever, passively, They also reshaped that. So, there was a kind of a transmission and transformation, okay, or transmutation. Now, let us take these transmutations and look at them. I know I'm rushing through this, but, I'm just trying to give this broad picture of the circulation. Now, the Greeks thought of everything beginning with self-evident axioms, okay? That is, knowledge was beginning. Aristotle believed in it, Plato believed in it for different reasons. So did Euclid. We don't know whether it's influenced by Aristotle or Plato, but whatever it was, the knowledge in geometry began with self-evident principles or first principle. And then you derive the cause-effect relations from them. Now, now for the Europeans at that time, because of their Christian beliefs, the idea of other sciences, including geometry, should be modeled on this was problematic. Because if the first principles are self-evident, even God could not have made the first principles of any discipline other than what it is. He had no choice. They were necessary principles. And this would be a direct attack on God's omnipotence. It was greatly debated at that time. Someone like Thomas Aquinas was brought in to settle this issue. And he solved the problem by saying, for the sciences, the regularities of nature do not begin with self-evident first principle. They are God imposed, they're laid down by God, whatever, and then, and if they are laid down by God, it cannot be self-evident. I can't pick it up and say, this must be the way God must create the world, okay? And so it was more important for me to look at what were the laws that were laid down by God. And so, you have to discover it empirically. Now, and this is where I'm not using a term that Aquinas used, but the change was made with Aquinas to say the first principles of the science have to be obtained by observation. They are inducted axioms. So from self-evident axioms to inducted axioms was a very major change, okay, that was significant for modern science. Okay. And so this was an epistemological change in a way. Now, the same thing happened with Arabic optics. We know that for the scholastics, and the Arabic optics was very, made a big major impact. But it went on to influence Renaissance art. That is this excellent book by Hans Galpin about how the pictorial perspective of Renaissance art came from changed the visual theory of algebra, perspectiva, into a theory of how to make pictures. Okay, so you drew lines, the rays of light came in, so that and it had a big impact because it said that accurate, unbiased observation of nature is possible, and we can be confident that what we see, if we see it in a perspectival way, kind of, represents the world as it is. What appears is, in a sense, what is. And this is the idea of phenomenal realism, provided you looked at the world in a certain way through perspectiva, using geometry and optical theory of algebra. And this led to phenomenal drawings and anatomical drawings, like with Vesalius, moon relief maps, like we saw with Halifax's Selenographia, engineering diagrams which were drawn in perspective, okay, and so on. There's a very different way of representing nature. And nature, as it really is, and as it actually appears to the eyes. And this is a change from the mathematical realism of Al-Haytham to a phenomenal realism. Trust in the senses, which is quite important. Okay. Now, another thing happens to Indian numbers too. They don't get transformed. We still use the same decimal place number system with 0. Now, probably it's the only language that is universal across the world. Okay. And the reason for that is it turned out to be very powerful for science later on. Now, the famous historian of science, Alexander Coyle, said, the ancient mathematical theory of Democritus was not useful, we couldn't develop a mathematical theory because it was a sensual theory based on sensualism. We thought of atoms as having angularities, you mean that you get a pokey feeling or fire feeling, or being smooth, or the size of the atoms. We thought of them as geometrical atoms, geometric terms. Okay. But our modern science, at least at the time it developed, early modern science, was based on a dynamic concept of atomism. The atoms, created pressure, variations in pressure, temperature, and so on, because of their motion. Descartes was the first to introduce this, and that the motions of atoms as they collided with each other conserved the original quantity of motion that had been put into the world by God. So the quantity of motion had to be conserved, and we talk about quantity of kinetic energy has to be conserved. Now, all of these conservation laws cannot be framed geometrically. They have to be framed algebraically. We write algebraic equations, we equate and we try to balance. So energy in the beginning must be equal to the energy at the end, and so on. And there have been a number of writers who said, well, these, dynamic atomism requires this kind of algebra. And of course, algebra with the number system and in generalization came from the Indian number system. And dynamic atomism is only possible by generalizing, I think there's a spelling mistake there, mathematical atomism by using algebra to frame, the laws of mathematical of atoms. There's something wrong with the line there, right? But there is a change again here, okay? That is the mathematical atomism of the Indian number system, which is kind of a conceptual thing, has now become a dynamic atomism. Okay. And finally, Chinese technology. They also had an impact. Okay. I said earlier that they were based on contextual experimentation, working within the context. The big debate in China between the Confucians and Taoists, should we follow, leave nature alone, go its own way, or should we cultivate nature? This is part of the whole idea in Chinese philosophical debates. But Bacon himself was impressed by those technologies of the Chinese, but he recommends that we should do something more than just tinker with, systems to improve them, to perform better. He says we should torture nature and constrain nature, do experiments, creating conditions that were never there in order to understand nature. Now, why did he do that? Because he wanted to discover the regularities in nature, the laws that were there, which we can understand by induction. The Bacon introduced it. Possibly I'm wrong, but he definitely uses the term induction for this. Okay, So you experiment by putting nature into constraints, okay? And this is a big shift. It's a shift from the contextual experimentation of the Chinese. Even Aristotle, I think, believed that you shouldn't violate nature's context, to the coercive experimentation of big. Environmentalists may not like this, but this is what happened with that shift. Okay, so there again was a big methodological shift. So these were four traditions entered, and their methodological orientations got shifted, but they were not, the shift could not have been made without the original. So in a way, I would like to use the word transmuted, okay, like a mutation within a gene. Okay, now to illustrate this is where I feel a bit more nervous, okay, because I don't know if I'm forcing these conclusions into Newton's treatises or whether I'm actually extracting them out of it, okay. But Newton actually did not begin with self-evident axioms. He began with inductive axioms, okay. And in his optics, he actually presents 8 axioms. He lists them down, okay, about performance of light, especially as it went through prisms, in his experiment, the regularities, the law of reflection that we now know was one of his axioms, and so on. I won't go through the 8. But how did he get to his axioms? He got to his axioms through observation and experiment. He was very insistent on that. I mean, inducting them from the phenomenon and seeing. Okay. In Principia also, he lists them as axioms. He's trying to follow the Euclidean style, but if you look at what he's actually doing, you realize Newton's axioms are not self-evident. They are inducted from the phenomenon as he sees them. From his observation, he derives these principles. Okay. In the Principia, the axioms are laws of motion, basically. Okay. The 3 laws of motion, not the law of gravity. Now, Newton also, this is the Arabic optical tradition. As I said, Newton's phenomena are Kepler's laws of planetary motion. Many people would disagree with Newton about this, modern philosophers, but I'm just going with, he said, they are my phenomena. So I said, okay, they are derived from observation. And he derives in some convoluted way of approximations his axioms from the phenomenon. Okay. And then he didn't think that these laws were hypothetical laws. It was not just framed as a hypothesis. He said hypothesis is nothing to, I claim no hypothesis. Vis-a-vis gravitation, but also in general. Okay. So we can say that Newton, what happened in art? The change from, the mathematical optics, of Alhazen to the optics used, in painting and so on, to see the world as it really is. Newton adopts a phenomenon, realism. Okay. Now, the next thing was we talked about atoms as being dynamic and in motion. Now, Newton actually also believes in the atomic theory. He believes, but he doesn't say this is what is the case, because they cannot be, but his mode of analysis is very atomistic. His mode of analysis is very atomistic. That means when he thinks of motion of a body, gravity, he first says, okay, the gravity can be seen as 2 bodies point to point, the sun's center and the earth's center, and what is the gravitational force. And then he does another approximation, he divides the earth and the sun into little parts, and then sees how all of these parts of a gravitational impact and this of a gravity, and they come to, and you add them up and they come together and so on. But finally, you realize the center of gravity is all you need. So you can assume that the whole mass is concentrated at the center. I may be oversimplifying this, but this is what I think he did, looking at, I didn't go through the details, but looking at kind of what he did. But I have a physics background, a physics degree, I think I understand what Newton did. So, but this is at least what we are taught, okay? So, now both kinds of, so Newton's atomism could be methodological or ontological, but both of them involve conservation laws. And for conservation laws, you need algebra and so on, and if you need algebra, the Indian mathematics number system comes in. And so Newton embraces a mathematical dynamic atomism. I think I skipped that. Yeah, the atomism, a dynamic atomism of atoms in motion and explaining phenomena in terms of atoms in motion for which you need algebra. So there's a shift here actually from the mathematical atomism of the Indian number system to a kind of a dynamic atomism and a welding of them together, okay, in a way. Now, finally, we come to Newton's coercive experimentation. This is very easy to understand. Bacon said, put nature in constraints, torture nature, put nature in conditions that were never there. Okay, Newton does this to understand the world, to understand light. He puts light through prisms and it bends, and he studies the bending. And then he says, it bends and comes out as a spectrum of red light and, blue light, whatever. And then he takes the red light part and puts it through another prism and says, oh, when the red light goes to the other prism, it still bends the same way, okay? And he's forcing light to reveal its secrets through this kind of method applied in different situations. So this is coercive experimentation, okay? To prove that there is such a thing as absolute space, Newton hangs a bucket, and then he puts some water in the bucket, and he whirls the bucket. And after the whirling, the water also whirls with the bucket and finally forms a sort of a concave surface from the top. And he says, look, this motion, the water is not moving relative to the bucket. Nevertheless, a concave shape. Why does that happen? Because it's rotating relative to absolute space. The space is something that really exists and it's absolute. Okay. So he does these experiments. So there are all these excited pendulums and so on. So this is Newton's method. They exemplify coercive experimentation. Okay. Now, and in a sense, because he does all this together, we see him as integrating these four methods of four modes of knowledge that came from different parts of the world, but were transmuted, and then combined. Of course, the whole process is a very complex process, but it exemplifies what we have seen. Now, finally, I wish to end by saying, our conference is about circulation of knowledge and its implications for science and technology studies, science studies, history and philosophy of science, and so on. How is this relevant? And I think the speakers have talked about circulations of knowledge across Eurasia, circulations of knowledge between scholars and practitioners and so on, all kinds of circulations, and that we need to include this wider global context in the history and philosophy of science. But when we began, we saw people like Floris Cohen and Toby Howe, who are leading historians of science and writing quite recently, not more than 2 decades ago, don't see it this way. They see history in terms of running in tunnels. There is a Chinese history tunnel, Sinocentric. There is a European history tunnel, Eurocentric. There is a Islamocentric tunnel with difficulty, people are trying to construct Islamic science or Islamic knowledge, whatever. And there's a Indo-centric tunnel, which some people are trying to construct, but not quite that successfully either. But I think it is important to recognize that this way of looking at things, is no longer really possible because of the way the history of science and the philosophy of science has gone on. Now here I've talked of, how there's a history of science and transmission of updates and other disciplines and other systems and so on. But we also think of the transmissions as also transmitting modes of inquiry that became reshaped. So the implications for, and we can see this, we have no hesitation about saying the Greek tradition, because we take it to have contributed to modern science, which it certainly did. We have no hesitation thinking of the Greek tradition as giving us knowledge of certain sciences. We have no hesitation of taking the Greek tradition, giving us certain methodologies that went into modern science. But there's great reservation about connecting the tunnel, from other traditions. And so this is, just a kind of a way of narratizing, the history of science from a circulation perspective. But if we accept this, then when we think of the history of science, we have to globalize. The other traditions become relevant. So that we need to take their formation, their transplantation into modern science, their transformation, and how they shape modern science seriously. The next thing that we have to do, we also need to take the philosophical context from which they emerge. We take Greek philosophy seriously, ancient Greek philosophy, because we see it as having contributed to our modern scientific tradition. But if these other traditions also contributed modes of knowledge that came to be integrated into the methodology of modern science, then their philosophical traditions also become important. We need to take, say, Moism seriously for its contextual, experimentals. We may have to take Aryabhata's astronomy seriously because of its impact on Indian astronomy and Islamic science, Madagascar school astronomy, and so on. And also the Greek tradition. We shouldn't negate the great achievements of the Greeks. Mihira, 7th century Indian astronomer, said, even though the Greeks are, strange word, barbarians, we must respect their sciences, So, everyone called everyone barbarians in those days, so it's not really that offensive. So it's nice to be a barbarian because the barbarians conquered all of them later on. So this, so what I would like to finally end with, since I do have some couple of minutes, is, when I went to the exhibition, we had the visual exhibition, it gave me an idea to include these images. I will talk about Henry Billingsley, right, who translated the Euclid into English. Well, here he has arithmetica. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which Euclid never knew about, but it's in his Euclid text in English. And Musica, Astronomia, and so on. Hipparchus who came before Euclid, and so on. Now, similarly, we can also see you know, in the selenograph here, the front is peace. Here is Al-Hazar, underneath is reason. Here is Galileo, underneath is sense observation with his telescope, okay, and with his stroke. And here you have the Indian numbers from the Margarita Philosophica 1503, where you have you know, that Pythagoras working on the abacus, which you probably never did, and Boethius using the Indian numbers, okay? And finally, you have Bacon, you know, 1620, you know, with those galleons sailing out across the Straits of Pillars of Hercules, across the Straits of Gibraltar. So there were a lot of these connections with the rest of the world that were actually recognized by Europeans, you know, not only in the Middle Ages, but also later in early modern science era, that could actually teach us a lot about how we can develop this circulation of knowledge idea and embedded it into the history, but also I emphasize philosophy and possibly also sociology of science, because there is a change of social context, where, you know, that you have to take into account. And with that, I will conclude my talk. Thank you.
My partner does a lot of dog sledding when she's up north. That looks very smart. I guess it behooves me in the last couple of minutes is say a couple of things about this, and then maybe go to some questions just of us in there thinking. It's really important for a conference like this to encounter the works of Florence Cohen and Toby Huff, or maybe the popularization of Neil Ferguson and others that talk about civilizational stories. And it's usually a one-way street. But the history of ideas that we got on this grand narrative, historians of science are sometimes rather unused to, or even think that they might have surpassed, and certainly resisted sometimes. If we want to dig into the grand period, one of the things that we'll have to talk to our people about when we're in our conversations at lunch or in the later, what do we do next, is not only these grand archetypes of knowledge that encounter each other, but rather to look at those crossroads. And Europe was in the middle of the crossroads, which is now becoming the globalized street, very negligible that that Europe is but a bunch of trails and silk roads and encounter and bring these ideas and these techniques to encounter one another. But that's maybe where a project like yours has to move. And I know that you've been thinking about these things, like how does the ship material that comes from India take certain kind of passing mathematical techniques into here. We'd love to hear a lot more about that. And about how the possibility of these encounters creates the messed up archetypes of what it is to be knowledge, and turn away a little bit from thinking that Newton himself is a crossroads, although the 1931 great conference, History of Science, that produced Crossroads of Science by the Soviets, began to think along these material and actual cultural encounters. In there, perhaps we can rethink the civilizational model, and in something that you're saying, maybe in these crossroads, that we can rethink the idea that center periphery models, which they don't dominate our field so much anymore. There's certainly that which is the ground upon which most discussions happen about the building of modernity and the trajectory of modernity in only one direction. But I thought I'd a disclaimer or push back. If there's any questions, we have now 47 seconds. 46 seconds. Okay. go after it at break, and we'll come back to our separate rooms. And for our seminars or sessions, and then we'll come back here for the final.